Hello students, in today's class we will read the third case for the topic of potential energy in an external field. Here the potential energy of a dipole in an external field will be defined, and we will read how these external fields and these internal fields developed due to the dipole itself are making an important role in the dipole configuration. So we know what is a dipole. Dipole is a small system in which we have one positive charge and one negative charge separated by a distance of 2a. Both positive and negative charges are of equal magnitude but of different polarity. Both the charges have equal magnitude and different polarity. Polarity states here the sign of these charges. If one is a positive, other one is a negative charge. Then for a particular dipole, we can define the dipole moment. Dipole moment is denoted by small p, which is equal to the distance between these two charges, or the length of dipole into the charge of dipole. Charge of dipole is q and 2a is the length of our dipole. Length of dipole is very small. We define dipole for a very small length basically. These dipoles, we cannot segregate positive and negative charges to bigger distances or bigger lengths. So dipoles are usually a smaller entity. Now we'll come to our topic. These are the basics of the topic here. Basics. If you do not know what is a dipole, then it's useless to study next point, that is anything electric fields relation with a dipole, potential energy or work done in keeping the dipole configuration stable, and any other concept related to dipole. So it is very much necessary to understand dipole, and these dipoles are created only when there is a positive and a negative charge present. A positive and positive charge will not be able to create a dipole. A negative charge will not be able to create a dipole. Dipole needs equal and opposite charge into the system. Now we are considering a dipole with charges q1, that is equal to plus q, and q2, that is equals to minus q, placed in a uniform electric field. They are placed in an uniform electric field. This electric field is external. This electric field is external electric field. As we know this is external, we are not mentioning ext everywhere. So it should be very much clear, wherever we are using E in this concept, we mean the external electric field. And this external electric field is coming from some source away from our system, which is strong enough or held at that point by some unknown forces and is able to produce its effect in this configuration of dipole. In a uniform electric field, the dipole experiences no net force. Now our E is uniform, so what exactly happens? Whenever your speed is uniform, neither you decelerate nor you accelerate. You will be walking on this straight line as you are going normally. Like if you are accelerating it or decelerating it, you will increase or decrease the speed. But when there is no such acceleration, there is no increase or decrease in the speed. Similarly, when this dipole is kept in the uniform electric field, this dipole will attain, in the starting when we are introducing, so this initially will try to come along with these electric fields. This dipole will try to come with these electric fields. Once it attains that position where this electric dipole is stable in this electric field unless until we are not changing this electric field, the dipole will not change. Dipole will become a stable dipole, So in uniform electric fields, dipole tends to take a stable position. But though there is no net force, because it became stable, it is not exerting any force in downward or in upward direction. It is here in this particular stable. Like if you are sleeping properly, why will you change your configuration of your sleep? Okay, you will sleep in that particular position only. If you are not comfortable, then only you will try to change your position, right? So this dipole is also stable, so it will not uh, experience any force on it, and it will be stabilized, but it will experience a torque. How come it's going to experience the torque? Torque will be like, torque is a rotational force which is due to the dipole's moment and the electric field which are introduced in this. So this torque will be given as tau equals to P into E, P cross product E. This one thing should be remembered very nicely, that our torque gives us cross product of P and E, Now if we want to find the magnitude of P cross E, then we have to remove the vector component. To remove that, what we have to do is PE into sine theta. The removal of cross product will give us sine theta, right? So this will be our torque that is being experienced by the dipole in the given uniform electric field, which will tend to rotate it unless P is parallel or anti-parallel to E. Why they are saying so? The torque will be faced by this electric dipole, because the torque is dependent upon the two points. One point is P, see over here, one point is P, other point is E, and both are having cross product. So sine theta, if we take sine 0 degree, it is 0, sine 90 degree, it is 1, and sine 180 degree, it is again 0. So we will assume the first case. Our tau gives us P cross E, PE sine 0 degree, PE sine 0 degree, PE sine 0 degree. Sine 0 degree is 0, so the whole torque will be 0. In this case, it will not face any torque. What is this case? This case is P is alone E. P is alone E. Both are making an angle of 0. Another case for the torque is PE sine 90 degree. Sine 90 degree is 1. So the answer will be PE. PE. And this is the position where our P and our E are making an angle of 90 degree with each other. This is the point where our dipole will face torque of the maximum magnitude. Now we will see the third case. Tau equals to PE cos sine 180 degree. Now sine 180 degree is again 0, and the answer we got is 0. In this case, what is the case? P and E are in opposite direction. P and E are in opposite direction. That implies they are anti-parallel to each other. Though they are parallel, but their direction are opposite to each other. In this case also, the torque will be minimum. So to find the stable condition, of the dipole with respect to the dipole moment and the given electric field, we need to utilize the Torque's formula. And according to Torque's formula, maximum torque is faced when electric field and the dipole moment are at 90 degree. But in case they are parallel or anti-parallel, to each other, the torque will be zero. Torque will be zero. Now, suppose an external torque, tau external, is applied in such a manner that it just neutralizes this torque and rotates it in the plane of paper from the angle theta naught to the angle of theta 1 at an infinitesimal angular speed and without angular acceleration. What exactly we aim to do at this point is that this configuration is having some internal torque due to its own dipole moment, that is internal, and from the external sources we are providing tau external. This tau internal is almost equal to tau external. Please make it is almost, not exactly. Tau external is having a magnitude that just neutralizes the effect of internal torque and helps this dipole to move in such a way that it when it is making an angle of theta degree, this is E, this is P, this is our dipole, right? Plus Q minus Q, this is our dipole, right? So this is making some angle of theta naught, and tau external we have provided in such a way that it will neutralize the internal torque's effect, but still will create a little difference, and in this little difference our angle will either reduce or increase. Anything can happen, but by a factor, very small factor. So the change in angle is from theta naught to theta 1. Change in angle is from theta naught to theta 1. Okay, so now this is what the condition we have taken. The change in angle is from theta naught to theta 1, and there is a little angular speed, but no angular acceleration. The system is not accelerated. If in case we are accelerating the system, then there will not be any concept of existing uniform electric field. A uniform electric field implies no acceleration, no deceleration. There is no effect on acceleration of this system. Okay. Now the amount of work done by the external torque will be given as W equals to integral from theta naught to theta 1 to tau external theta d theta. See, work done W equals to integral over theta naught to theta 1, because change is a change in angle is from theta naught to theta 1. So we can integrate from theta naught to theta 1 tau external into theta of d theta. Now tau external is given as Pe sin theta. Tau external is given as Pe sin theta. Pe are constant. A constant value cannot be differentiated and cannot be integrated. Okay, constant. So Pe will remain same, and the integral over sin theta is cos theta plus some constant. Okay, that is what we have read, right? So introducing the cos theta here and taking these limits from theta naught to theta 1, we have applied. So the work done which we received is Pe cos theta minus cos theta 1. Pe cos theta naught minus cos theta 1. This is, again we are solving it further. So the previous equation I'll write on the top. What we have got, W equals to PE cos theta naught minus cos theta 1. This is the value we have received so far. We will aim it as a equation star. Now what usually in general when we are not dealing with dipole, what we do is that at infinity we take u equals to 0, potential energy equals to 0. In this case, this is the work done. So after defining work done, how can we define the potential? Potential energy stored in system. Potential energy stored in system, that can be defined as PE cos theta naught minus cos theta 1. Same, potential energy stored is equal to the work done. Okay. Now, as we have taken this one, our potential to be 0 at infinity, in this system of dipole, we similarly want to take a point in the space that gives us potential energy to be 0. How we are going to define it? Let's go through. This work is stored as potential energy of this system. We know that. We can associate potential energy u theta with an inclination theta of dipole. Potential energy at point theta naught equals to pi by 2 is taken to be 0. Here theta naught, if it is equal to pi by 2, that is if it is equals to 90 degree, that is equals to 180 degree divided by 2, 90 degrees, then the potential will be 0 here. We are taking, this is the point in the dipole's space where our potential energy will be 0. When the inclination is at 90 degree, potential energy will be 0. So our equation, the equation of work done which we have wrote over here, see the star equation will be converted to this equation. Potential energy stored in the system, this is given by potential energy stored in the system equals to u theta equals to PE cos theta 1 taken as cos theta not taken as cos pi by 2 minus cos theta. So cos pi by 2 equals to cos 90 degree. What is the value of cos 90 degree? It is 0. So this term will become 0. 0 minus something will be this something only. So answer we will get is minus PE cos theta. Minus PE cos theta. If we are removing this cos theta, it will give us a dot product. I have explained in the previous lectures how we take a cross product and how we take a dot product. So when this cos theta is removed, it gave us a dot product. So the potential energy of a dipole is given as P dot E. P dot E, dot product of vector P and vector E. Now applying the equation representing system of charges for plus q and minus q. Here we were just reading about the dipole as a single entity. Now we are defining it for the system. Our first point in the system is plus q charge and our second point is the minus q charge. In that case, potential stored will be given by u dash of theta, that is equals to q. Q is the same magnitude for both the charges of the dipole. Like we have read many times, our plus q and our minus q both have equal dipole, equal magnitude, though their polarity is different. Okay. So u dash of theta gives us q into v at r1 minus potential at r2 minus q square by 4 pi epsilon naught into 2r. This is potential due to one charge at second charge placed at a distance of 2a. See over here, it is 2a. In this system, this is minus q, this is plus q. We know potential of this charge we will define. It will be given as q upon 4 pi epsilon naught into r1. Now work done will be given as q2, this charge, into potential due to first charge. So it will be equals to W equals to q2 q1 upon 4 pi epsilon naught into the distance between r2. Here q1 and q2 both are q, so q into q square. r12 is 2a, the distance of a dipole, the length of a dipole, into 2a. So this is from where we are getting this second term. Okay. Now going further, we will see the potential difference between the position r1 and r2 equals the work done in bringing a unit positive charge against the field from r1 from r2 to r1. What exactly they are here trying to say is that the potential difference of these position r1 and r2 is equal to the work done to bring any kind of positive charge against the field from r2 to r1. Whatever field is coming from r2 to r1, there is some force will be there due to this field, and this will actually try to repel the positive charge. Now this positive charge is a test charge which we are bringing from infinity to that point in between the charges q1 and q2 of the position vector r1 and r2. Now to find the difference, how do we find potential difference of a system? In that particular system we will introduce a test positive charge, and whatever amount of work we need to do to bring that test positive charge into the system will give us the potential. We know work done equals to charge into the potential, and from this basic information we can find out how much potential is produced due to the system. Now the displacement parallel to the force is 2a cos theta. Thus V at R1 minus V at R2 will give us E into 2a cos theta. See, potential equals to E into S. S is displacement. E into S. Okay. So here the displacement is 2a. That is the distance between these two charges. But is our dipole always in the lateral position or vertical position or longitudinal position? Isn't it a rotational one? Our dipole is a rotational one. It makes a position at some inclination, at some angle. So giving this value of the displacement only with the help of a number will not help us. We have to introduce the angle also at which this dipole is inclined with the electric field. We have to give the angle at which our dipole is inclined with the electric field. So 2a cos theta is the value of S. So the potential we found as minus E into 2a cos theta. Now u dash theta equals to minus Pe cos theta from the last equation, minus q square by 4 pi epsilon naught 2a. This equation turned out to be this, and this equation came here as such. Now cos theta, PE cos theta is converted to P dot E. See, here we have seen from the first equation of this page. This first equation, equation number 3. See, I have written here. This came from equation number 3. This value came from equation number 3. Minus Q2 Q square by 4 pi epsilon naught. This term as such over here. Okay. Coming to this point, here we note that u dash theta differs from u theta by the quantity which is just a constant for the given dipole. This quantity is taken as constant because there is no such variable. Okay. And this equation 5 and this equation 3 differ only by this constant quantity. Since a constant is insignificant for the potential energy, we can drop second term in the equation 5 and it reduces to equation 3. If we are negligibling it and making it 0, what will happen is we will get equation similar as 5. 5 will become, equation 5 will become same as that of equation 3, same as that of equation 3. Okay. Now how can we do is that while at theta naught is taken as pi by 2 for making the potential equal to 0. Here we have seen to make the potential 0 we have taken theta for making u at theta equals to 0. The theta taken was pi by 2. Why so? Here is the answer. The work done against the external field E in bringing plus Q and minus Q are equal and opposite. We need to do the same work because both are same in magnitude, but the polarity changes. And at theta by 2, it cancels. At pi by 2, this value gets cancelled out. Q at VR1 minus VR2 will give us 0. Answer as 0. So potential over here and the work done over here will be 0. At theta equals to pi by 2, this work done will be given to be 0. So in a case where there is no potential existing, will only be the point where work done will be 0. Like if there is no force on you, the progress you are showing will be reduced out. But if there is a force on you to do something, your potential will come up and you will try to work faster and more efficiently. That is how we see. So in this particular dipole, what exactly happens is, here is our minus q and here is plus q. These at all the theta, these are giving us some amount of work done. Okay, at theta equals to pi by 2 at 90 degree, what is happening, the amount of work done to bring this side or that side, the dipole to this side or that side is 0. Our dipole is having all the freedom to move all around at the value of theta equals to pi by 2. So work done against external field is equal and opposite at theta not equal to pi by 2, and because it is equal and opposite, it cancels out, giving us a value of 0. And wherever the potential is 0, there is no need to produce any work. There will be no stored potential energy also. So that is the concept over here. Hopefully you have understood. The main point which needs to be summarized over here is in our dipole, if E is uniform, these are the summary points. Just make a note of it. E is uniform. The net force working on it is 0, but there will be a torque equal to P cross E. And due to this torque, our system need to do some work, and because we are doing the work, there will be stored potential energy. For the given dipole, we have taken potential equals to 0 at theta naught equals to pi by 2, because E external at pi by 2 is equal and opposite for minus q and plus q, equal and opposite. So hence it cancels out. Hence it cancels out. So at this point our external field will be 0, hence potential will be 0, hence work done equals to 0, and potential energy stored by the system will also be 0 at this point. Hence we are taking theta not equals to pi by 2 where our potential is 0. So this is what we have read in today's class, and in next class we'll read something new and more interesting of a concept. In this particular concept we just went through all the requisites, and that's all for today's class. We'll meet up in the next class. Have a good day. Bye bye.